seeing everything now?
Yeah.
All right. Okay.
The phone is not clear.
This is not clear?
I can really hear you.
Yeah, just kind of zoom in a little bit on it, at least for now. Are you recording or not? Not yet. Oh. I didn't know. I was like, oh, I thought you. Okay.
I'll add it.
Yeah.
Okay, no problem.
Okay, so now we're going to take a look at the Discovery TGA. TGA stands for thermogravimetric analysis. So basically, what that is that you're testing or you're looking at a variation or change in weight over time and or temperature. Okay, so in essence, it's just a very, very sensitive scale that's essentially has a furnace attached to it that can control the temperature. Okay. What it can do is sort of a list down here. First of all, you do have a temperature range from ambient up to a maximum of 1200 degrees Celsius, depending on the type of pan or sample pan that you use. We don't have any cooling system, so this is all air cooled. So that's why you can only go to ambient temperature. You can't go below ambient. The instrument itself can go through experiments such as looking at the thermal stability of the materials, oxidative stability of the materials, compositions of systems. They say multi-component systems, but that could mean two different types of materials in terms of solid and liquid or solid and solid, depending on what their degradation temperatures are. If they're pretty far apart, it'll be really easy. If they're a little bit closer together, things get a little bit more complicated. But it does have the ability to determine, how much of each component exists based on the thermal stability of each component, right? You can do kinetic analysis with this instrument, decomposition kinetics. You can look at lifetimes by doing sort of an extended experiment using the decomposition temperatures at varying rates and things like that. That would require a few experiments in order to do that full analysis, but it is something that's very possible with this instrument. And of course, you can do things like identifying moisture content and volatile content of materials. Again, the reasons why these are all possible is because each one of these constitutes some sort of change in mass of the material, which will be picked up by the instrument itself at X temperature, and that will give you an idea of exactly what is happening to your material. So the instrument itself is right here. The power module and computer is stored in here. So what we have is essentially this is a furnace. It is actually an IR heated furnace, so there are 4 IR and infrared bulbs in here. And I'm not sure if you can see, but there's essentially a metal hook hanging down vertically right in the center of this furnace. So essentially what happens is that on this auto sampler here, you would load your sample. You would tell it which sample position you're on. It goes from 1 to 25. And it will rotate and load your sample. And your sample will essentially be hanging from that hook. And the furnace will then move upwards and enclose everything. Within the furnace itself, we do have a gas flow that actually comes up through here, across, and the exhaust comes out this way. The gas that's typically flowing is nitrogen. We do have 2 gas ports, so we can switch gases in between the experiment. The second gas right now is air. So you can imagine nitrogen is generally an inert gas, so it doesn't intimately react with most materials that you may be running. But then air is what's defined as a reactive gas. So the oxygen in the air, for example, can react with materials and then change the decomposition profile of that sample. Okay, so unless you are looking specifically for the reaction of your material with a specific type of gas, we generally use an inert gas for your experiment. So nitrogen is essentially always going to be flowing until you switch the gas to gas number 2, which would be air in this case. Okay. Of course, we do have the ability to change what those gases are. However, if you would like to do that, you'll have to let us know so that we can get a separate tank for you of whatever specific gas it is you're interested in. And then we'll connect it to the instrument and run it that way. All right. So in here also we do have a thermocouple, which of course records the temperature. The thermocouple is actually coming up from the bottom, and so it'll stop, just directly below the sample pan, and that will give you the sample temperature. So that would therefore govern how much power is sent to the IR bulbs, and that's going to give you your temperature reading. Now, right below here is actually a secondary. It's another sample pan, and this is actually the reference pan that's in here. This reference pan is essentially what's going to give you that accurate mass measurement. So you're not necessarily measuring the mass of one thing, you're actually measuring the mass of two things. So you're measuring the reference mass and the sample mass, right? And essentially what you will do when you set up your experiment is that you would need to cancel out the slight difference in masses between the reference and the sample, such that the only mass that would be recorded would be directly from your sample, right? And this is essentially, the reason why there is a reference pan here is that this is essentially a counterweighted system. We have a diagram up there of what the inside of the instrument actually looks like. So you can see that both on the left and the right hand side, there are two hooks that are suspended vertically, and so that will essentially rotate back and forth based on the mass on each side, and that the sensors in there will determine exactly what that mass is. So on the left hand side will be where the reference is hanging, and then the right hand side will be where your sample is hanging.
So it's
all right?
relative, right?
Excuse me?
It's relative.
Yeah, so it's the relative difference in mass between those two things. That's what's actually going to give you your sample mass, right?
Sorry. So the thing is for the reference mass, the reference pan which you're talking about, and the one which you put the
should be the same. Yeah,
should be the same. But like with time to time,
there's slight differences. So when you do your experiment, as I'll show you, the first step would be to tear the pans, which basically means cancel out that slight difference between the reference pan and the sample pan. Once you do that, then essentially you're going to start from zero mass. So once you put your sample in, then it will only record your sample mass. Yeah.
Can you say again the function of the reference pan?
So it's that's how it's actually it's measuring it as a reference weight, right? So it's a counterbalance system, right? So if one's heavier than the other, it'll tilt to one side, right? And that tilting corresponds to a specific mass of material.
So the difference between these two, between the reference and the sample. Right?
Yes. Yes.
And then.
So that difference. For example, if I have an empty sample pan, right? My reference pan is always empty, right? So the reference is just an empty pan.
Okay.
So if I have just a sample pan in here and my reference pan, then the only mass that you will detect is a slight difference between the two pans, right? Right. No, there's no sample in there, right? So the slight difference between two pans, because you can't possibly make two pans exactly the same. So there's always going to be some slight mass difference, right? So if there's an empty sample pan, then there should only be that sort of residual mass between the two, right? Now, before you start your experiment, you're going to cancel that out. So you're going to start from zero mass, right? And then when you put your sample in there, now the weight is going to tilt towards the sample side, and that's going to give you your sample mass. The sensors are going to determine that's what the mass of your sample is. Okay? So it's going to rotate. It literally is doing this, right? So if one's heavier, it'll drop down. If the other one's heavier, it'll do that. So once you have one side heavier, which should always be the sample side, right? It'll always tilt that way, and it will determine how much that is based on how much it's tilting, right? So that's why you have that counterbalance system, because that centerpiece will sort of rotate around, and you have sensors in there that will determine exactly how much that rotation is and what that mass equivalates to, right? So that's what happens up in here, in this box up here. All right. And of course, they have their own, ways of making sure these things are accurate. Of course, the calibrations and all that are done. This is also heated. You can see on here, it's heated to 35 Celsius. That's to avoid condensation and things like that up in here. It's also to keep the gas. There's also gas flowing in here. There's nitrogen flowing up here as well. That just keeps things stable and keeps condensation from happening and corrosions and things like that. So there's always nitrogen flowing up here. It's flowing at 20 milliliters per minute, and the housing itself is heated to 35 Celsius. Okay, so that just keeps things nice and stable to allow for the best type of evaluation of the mass that it can get. All right. Can you pause for 1 second? Let me see if we can. Hey, recording? All right. So that's basically sort of a description of what happens up in this portion of the instrument. Again, the reference pan is located down here. There are 3 screws here, that's just finger screws that you can remove, and you can see the reference pan and change it. We do only have 2 types of sample pans here. Both of them are actually made of platinum. For obvious reasons, platinum is relatively inert, and it's resistant to oxidations and things like that. So for that reason, I don't really change a sample pan in here with the pans that we currently have available. However, if you do want to use a different sample pan, for example, in order to get to 1200 Celsius, you need to use an aluminum oxide pan, okay, not the platinum pans. The platinum pans are only rated to 1000 degrees Celsius. The aluminum oxide pans are the ones that are rated to 1200 Celsius. So if you're going to use an aluminum oxide pan for whatever reason, you would then have to change this reference pan from what it is now to the aluminum oxide, empty, clean aluminum oxide pan, to then be able to use your aluminum oxide pan for your experiment. So essentially what I'm saying is whatever pan you need to use for an experiment, you should use the same pan for your reference. And that applies to pretty much all thermal analysis equipment, whether it's DSC or TGA. You want to use the same reference pan as your sample pan. Okay, so the same thing applies here as well. All right, they've made it easy access where you just have to unscrew this. You drop it down vertically. The pan will just be right there hanging. The only unfortunate thing is that you have to sort of manually remove it, but be very careful to manually remove that pan. Place it aside, put your correct reference pan in here, and screw it back up and close it up. Again, if you are using the pans that we have provided, generally you don't need to change your reference pan because these are all platinum pans. So those relative differences aren't going to matter very much. However, if you are going to use a completely different material, then in terms, for example, aluminum oxide or aluminum, they will then require you to change this reference pan to that specific material. All right. So on the topic of sample pans, I will just show you some that we have available here. Of course, over time, they get a little bit dirtier than you might expect. But I will also show you how to clean these pans so that you can get them as clean as you can possibly have to run your experiment. So right now, we have 2 sort of subcategories of pans. These are all platinum, okay? But there are 2 subcategories. So the ones that I defined are sort of all platinum, so they're all silver looking. These are just pure platinum pans, and these have a temperature rating of 700 Celsius. Okay, so when you go into the software, like I will show you later, you actually have to tell it what type of pan you're using. So these pans are simply called the platinum 100 microliter pans. Okay. These that have these black tips on them, these are also platinum. These black tips are an alloy. And the reason why they have these black tips on them is above 700 degrees, what happens is that these platinum pans and the hook that's on the instrument, which is also platinum, they actually can start sticking together. And when they stick together, they can have a problem removing the pan from the hook itself. And that actually can cause spillage. It can cause the pan to fall into the furnace, which basically causes a lot of other problems. So basically their solution to that was adding this black alloy to the top of the pan so that when the hook is under it and it's suspended, there will be no sticking of the pan to the hook. and therefore these are rated up to 1,000 degrees Celsius. Okay.
What's the temperature they gonna stick together?
I don't know the exact temperature at which they stick together, but I do know that it happens. An older version of these did not have these pans with the black tips on them, and I experienced a lot of sticking issues. So they're almost like trying to fuse together, basically platinum on platinum, right?
Okay, yeah.
So at higher temperature, they almost try to fuse together. So when you try to remove when the autosampler tries to remove the pan from the hook, it actually gets stuck,
Yeah.
right? Trying to lift it off, and you can bend the hook, you can tilt over the sample and spill things. You can drop the sample pan right down into the furnace. So all these things require maintenance and fixing. That is actually pretty problematic, especially if you start bending things and spilling things. So this was their sort of solution to that. Is you put this black alloy on top of it, it doesn't stick to the hook, so therefore it's rated to higher temperatures than the standard platinum. Of course, platinum as a material can withstand temperatures higher than that, but because of that sticking problem, that's how they came up with these. Okay.
That means it's better for us to just use the black one instead of
Not necessarily. Not necessarily. It doesn't make anything more accurate, right? Your accuracy isn't the problem. The problem is just that one little point of it sticking to the hook. So if you want to only buy these, I mean, that's okay. But considering most people don't really want to go above 700 anyway, especially if you're doing for polymer materials and things like that, then there's really no big deal in buying or paying extra for these than just buying the standard ones, right? Because these do cost a little bit more.
So
Right.
700 is like a
700 is a pretty typical value. If you're running organic materials, none of them will survive above that temperature for sure in any type of atmosphere. So it really won't affect your data in the case of whether you use the standard platinum ones or the platinum ones with the black tips. If you're doing organic materials, it's not going to be a big deal because you're not really going above 700 anyway. By the time you hit 700, everything's burnt up. Okay. Yeah. So that's the reason why they made these platinum pans with these alloys on top of them. And these are defined as the platinum HT, which basically stands for high temperature. So when you go into the software, and you're using these, you want to say platinum HT. You could, of course, just say standard platinum if you don't need to go above 700. But if you do need to go above 700, you definitely have to define them as platinum HT. Okay?
Do we need to buy this or?
No, we generally replace these every once in a while. These are reusable, so I'll show you how to clean them. But we generally replace these once we realize they're getting a bit old, like some of these are right now. We probably throw these away and purchase some new ones. Okay? So generally, you don't have to buy these that are in here. But if you do need a different material, like you want to buy the aluminum oxides and things like that for specialty types of experiments, you either will purchase those on your own, or you can actually use the Q600 to run those experiments as well. Because the Q600 sample pans by default are aluminum oxide. So if you do want to use that, we could just switch off to that instrument. So you have these options here. If they are in this little petri dish, they are assumed to be clean, so you can use them. If you don't trust people, then you could always give them a quick clean before you use them, and then you be on your way. I would always advise sure to give them a really quick clean off before you use them, just to make sure that the person who came before you did what they were supposed to do. All right. But these are always available. They're always right next to the machine. So feel free to use them. And of course, if any of them are looking too dingy or really bent and things like that, let us know. They can get bent during the cleaning process. That's actually very important because, as you can see, it has to fit specifically on this one point on the hook. So if they're bent up and that doesn't happen, again, you can cause spillage and waste your sample, things like that. So when we go through the cleaning process, I'll show you how to sort of be careful to not bend things up and destroy the sample pans. But essentially, that's the sort of inner workings of the instrument. Not terribly complicated. There is an auto sampler. So all you're going to really have to do is place the empty pan on the auto sampler, tear it, When it's finished tearing, you remove it, put your sample in there, and you hit go. All right. So in terms of sample preparation, it's very simple. Now, of course, if you have specialty samples, for example, you have something in a suspension with a bunch of solvent in it, you want to be careful to not spill anything over in the pans. If you're not going to very high temperatures, we have a method where you can put a DSC pan on top of this platinum pan to give you a bit more depth and volume, especially if you're doing liquid samples. That way, you guarantee that it's not going to spill over on you during the experiment. But these are just sort of nice ways to accommodate different types of samples. Okay, the general process of doing everything remains the same. Okay.
What if the sample spill into the furnace?
If the samples spill into the furnace, depending on what type of sample it is, generally the process is to essentially burn whatever is in there. So you raise the temperature to about 1,000 degrees in air, and you just burn away everything, and that generally cleans out the furnace. So that would be, the purpose of the people working here would be to do that every once in a while to make sure that the furnace stays clean and well maintained. That just helps flush out anything that may have spilled in there, and any residues that may have started coating the inside of the furnace and things like that. They'll get burnt out at 1,000 degrees in air, again, not in nitrogen, but in air. And that just keeps things clean. If it is something that can survive those temperatures, then you would have to physically remove the furnace and sort of clean it out physically. That takes a bit more work. But again, that's not for the standard user to do. That's for someone who's working here to do that. So if you do spill something in here, please let us know. And then we will go in there and do what we think is necessary to get it out. Okay. Just remember, anything, again, that's in there can get on someone else's sample. So be courteous. Don't try to hide and say, oops, I didn't actually spill anything when you did. Just be honest and let us know so that we can accommodate and get things cleaned up for the next user. All right. So that's basically the sort of mechanics of how you do things. What I'll go through now is basically showing you the software and how to prepare an experiment and set one up. And then I will show you how to then physically prepare the sample by cleaning the pan, tearing it out, and then how to put your sample in the pan. All right? So we're going to go over here.